Right. So in last class, we have started our discussion on this low power VLSI design. So why low power VLSI design is so important? Because nowadays almost all the devices are driven by battery, right? And you want the battery life to be as uh, long as possible, right? So as a result, you have to do the basic computations or whatever you are doing in that device, but you want the power dissipation for performing those operations to be reduced as much as possible, right? So regarding the power dissipation, we have also seen that the power dissipation can be of the switching power dissipation, static circuit power dissipation, and also the short circuit power dissipation, right? These things we have discussed quite extensively during the our CMOS discussion as well, right? So just to discuss, like, what do you mean by switching power dissipation? Switching power dissipation basically given by this alpha CL VDD square into F, where you know the alpha is the switching factor or the transition factor, right? So here we have seen that this power dissipated is proportional to this VDD square, right? So if we can reduce this VDD, if you can reduce VDD by half, then the power dissipation would become 1/4, right? So that was the goal. By seeing that, we have seen that, like, suppose if you are plotting this normalized power dissipation with respect to the supply voltage, then you can see as you reduce the supply voltage, your power dissipation reduces substantially. But at the same time, at the expense of what? At the expense of increasing delay, right? Delay is increasing. But is there any way by which we can actually type of compensate, or we can do a trade-off between this delay as well as the power dissipation? Right. Regarding that, we have first discussed this variable threshold CMOS technique. So here, what we do, instead of using the transistor which have fixed threshold voltage, we use transistor whose threshold voltages are variable. So now, what do you mean by threshold voltage is variable? How can you vary a threshold voltage? See, once you fabricate a MOSFET, its threshold voltage is fixed, right? Threshold voltage of MOSFET depends on what? Depends on the oxide thickness, substrate doping, right? Then the phi ms, metal to semiconductor work function difference, on all this stuff, right? So once you fabricate that a MOSFET, your VT is fixed. However, we also know that for MOSFET there is one more terminal. The terminal is called the body terminal, right? And we know if we change the body bias, then the threshold voltage of this transistor can be modulated, right? So here, what we can see from this, this is a simple inverter, but in this inverter, the body bias, the body are not been connected with the source, right? But rather, these bodies are connected with a substrate bias control circuit. This substrate bias control circuit does what? It changes this bias voltages accordingly, such that this such that you can alter the threshold voltage of this PMOS as well as the threshold voltage of this NMOS. Now, how can you do it? Okay, suppose, when do you want the threshold voltage to be higher? Okay, this is an inverter detailed circuit. So it has two states. One is during transition, means one is during the on state or during the transition state, and the other one is during the static state, right? So during the static state or standby situation, one of the transistor would be off, right? So you want transistor threshold voltage to be higher in what sense? See, suppose earlier VDD was 3 volt. Okay. Now you have reduced the VDD from 3 volt to 2 volt, right? What is going to happen to its ID? ID reduce, because if it is, suppose, if you consider the saturation region, then it is VDD minus VTH square. So now you are increasing VTH. So what? But VDD you are reducing. You are increasing this. You are reducing this. What will happen to this ID? So ID will fall down. So that will increase the delay, right? So if there is any mean by which you can reduce the threshold voltage at the same, almost in the same level as you are doing this VDD, then what will happen? This ID level will keep intact, right? Then probably you will not lose much on the delay side. right? So how can you do that? That is what this circuit does. So during the on state, means when the transistors are conducting during that state, this circuit does what? This circuit lowers the threshold voltage of this PMOS as well as this NMOS. So lower the threshold voltage means the driving is increased, so less time or the delay would be significantly reduced, right? However, during off state, okay, during off state, what will happen? During off state, you want the threshold voltage to be as high as possible, because we have already discussed there is some leakage current which is called the static leakage, and which is primarily due to the subthreshold conduction. And for modern transistors, that is the major part of loss, right? So how can you reduce the subthreshold conduction? By significantly increasing the threshold voltage. Because, okay, so maybe I can give you, I have some time today, so I can give you some example here, so you can understand better from this. See, I have already discussed this plot earlier. Say this is ID and this is VGS, okay? So ID VGS for NMOS. So for NMOS, how the ID VGS would look like? Threshold voltage is positive. It look like this. Okay. This is linear scale. That means this scale is linear. This is also linear. Now what we have, we are doing some change. We are plotting this in log scale. ID in log scale. So then this plot would look something like this. Okay, this IDVG, this same plot would look in log scale like this. So this is 0. So you can clearly see, even when this VGS equal to 0, that means when you have applied 0 voltage to this NMOS, still you have some leakage current, right? So there isn't, whenever you have a leakage current, there isn't power dissipation. So the power will be dissipated. Okay. Now the more will be the more the leakage current, more will be the power dissipation. True? More leakage current, more will be the power dissipation, because VDD is fixed, right? Okay. So now suppose, okay, here if I have to indicate the threshold voltage probably would be here. This is the VTH1, right? Okay. Now if you reduce the threshold voltage, right, because here we have seen to increase ID you have to, and if you are reducing VDD you have to also reduce the threshold voltage. Now see what will happen if you reduce the threshold voltage. Say the same characteristics, but it will be shifted towards in the left. So now it has shifted towards somewhat in the left, right? Right. So you can see, what about the leakage current? This leakage current has significantly now increased. So whenever you reduce the threshold voltage, your leakage current has to increase. Okay. Now you could have also argued then why it is like this, why you are saying that it should be parallel to this. I could have also make like this and keep the threshold voltage or keep this sub threshold leakage same, right? You could have also done this, right? So this slope, this particular region slope is called the sub threshold slope. Okay, and there is a theoretical limitation for this sub threshold slope, which is 60 millivolt per. This is very important. 60 millivolt per decade, right? So what do you mean by 60 millivolt per decade? 60 millivolt per decade means, say, here to here, okay, here to here. If this is 60 millivolt, right, then compared to this current will be 10 times. Compared to this current would be 10 times. That means to change 1 decade of current means to make the subthreshold current 10 times, what is the voltage or VG that you have to change, right? So, and practically we really cannot go towards for modern MOSFET even 60 millivolt per decade. It will be a bit higher, say 70 millivolt per decade. And it is not very easy to reduce the subthreshold leakage for the silicon MOSFET that drastically. So that possibility that by changing the slope you can adjust the subthreshold leakage, that is not that way feasible, right? So we have an option which is this one, that is substrate bias control threshold voltage. So by using the substrate bias control threshold voltage, what we are doing, we are reducing the threshold voltage while the transistors are conducting to make ID higher, and we are increasing the threshold voltage when the transistors are not operating or the transistors are off to prevent the subthreshold leakage or power dissipation. That way you can reduce the power, right? So this is the what this technique is all about. But it is not that way easy, because because what you have to do when the transistor is on, then you have to sense it, right? Then you have to
Sir,
adjust.
here on means transition and off means static, right?
Uh, could you please say it again, because I'm not able to hear
Sir,
you.
here on means transition and off means static.
Right, right. Off means, yeah, means off in the static, in a steady state condition. Means when you have fixed it to either to say 0 or 1.
Or one. Okay.
Okay. At that time only you are not charging or discharging any capacitance, right? Right.
Yes.
Right. So what about in the next case? Next case that we have studied is the multi-threshold voltage CMOS. Here, instead of changing the threshold voltage dynamically, what we are doing, we have fixed two transistors here and here, whose threshold voltages are higher, and we have fixed transistors in between. Okay, this is basically implementing the logic part, and this is basically implementing the logic part, right? And this is sitting between these two transistors whose threshold voltage is higher, and for this the threshold voltages are lower, right? So basically it is performing almost the same action, right? During standby, the leakage current is substantially reduced because of this high threshold voltage transistor, and during on state you make the transistor width here significant, such that the drop across these transistors here and here would be negligible. So that is the reason what we can assume, that here drop is almost negligible, drop is almost negligible. So VDD is applied here, right? This transistors has threshold voltage lower. So that way the delay issue by charging discharging will not be there. Okay. The third one that we have discussed is called the technology mapping. So in technology mapping basically says something like that. Suppose if you have to design an 4-input AND gate, so one of the way that you could have choose is like this. Other way you could have choose this one. So which way you are going to implement? Okay. So here we are using all NAND gate, all these AND gates only, right? And you can see here 1, 2, 3 AND gates. Here also 1, 2, 3 AND gates, right? Then will there be any power change in the power dissipation, or will there be any difference in terms of power dissipation? So for that, here we see probably this and this. Here we are not looking at this moment, but we have to look for this alpha or the switching activity part here. Right. Now, how do you calculate alpha? So alpha can be calculated by this formula, which is PF into 1 minus PF. So what do you mean by PF into 1 minus PF? When power will be consumed in an CMOS circuit, when the capacitor this will be charged, right? Then only power will be taken from this VDD source, right? Now, when power will be charged? When there is a transition from 0 to 1 in the output. Okay. So if we know what is the probability of having 0 at the output, and if you know what is the probability of having 1 at the output, if we multiply these two, then we'll get the transition probability. So that is basically what we are doing. Switching probability is basically PF into 1 minus PF. So if the PF is the probability that the output would be 1, then 1 minus PF would be the probability for which the output would be 0, right? Okay. So here the a common syntax is this PA and PB. This PA indicates the probability of input A for having a value 1. PB is the probability that this B will be equal to 1. Okay. And PF is the probability that the output would be equal to 1. So if you now calculate, say, and these values are also given, PA, PB, PC, PD values are given, then we have seen from last class calculation that for this case, the total alpha is coming here around 0.099. Here the total alpha is coming 0.029. So obviously you can see here the alpha is less, right, compared to this design. So for this design, the okay, so this is actually the input reordering, but I was talking about this, but it is basically the same funda, right? Here, not only by altering the gates. But by also altering the inputs, you could have also see a change in this alpha. So this is called the input reordering, right? So last time what means, now what I am talking here is this one. Here we are changing the design itself, right? You can see here, this is basically one chain type, and here basically it is a tree type, right? Here if you change it like this, I think, do you recall what was the value of alpha for this case? What was the value of alpha that we have calculated last class? So yeah, if you calculate the alpha for this case, for the first one, it is 0.2449. Okay, the total value of alpha here, right? And so I think here we have already written, right? Okay, sorry. We have already written this one and this one, right? So this was the value of alpha. So you can see that by simply just changing how you can going to implement the same logic, you can significantly change the alpha. So you can significantly impact the logic design. I mean, you can significantly impact the power dissipation. Similarly, by changing the input ordering, okay, you can also significantly reduce the value of alpha or switching activity. So you can see here it was A, B, C, and it was this circuit was implementing A, B, C. Here we have changed it to B, C, and A, right? Here it is also implementing the same function, but see the value of alpha, right? There is a change. So by also changing the input ordering, you can also significantly reduce the power dissipation. So yeah, regarding, we have also discussed what about the dynamic power, what about the power dissipation in dynamic CMOS logic gate, right? Do you have any doubt here? Okay. Then other techniques like phase assignment. So here, suppose if you have a high activity node here and you are placing an inverter here, then after inverter, this will also become an high activity node. So whenever you are placing more high activity nodes, you have more power dissipations, right? So you can see here you are implementing this A bar B, here also you are implementing A bar B. But you have here two high activity nodes compared to this one. Same thing you can see for here. Both outputs are same. If you check, like outputs are same, but the number of the highly active nodes are significantly reduced. That means the power dissipations are also reduced. Next technique is called the pin swapping. So in pin swapping, what we are doing, suppose here the switching activity of A is highest compared to B, compared to C. Okay, so that means this input A changes quite fast compared to input B, right? Compared to input B, and even compared to input C, right? Then in that case, if you could have assigned also this transistor with input A, all maybe your friend can assign this input A to this transistor. But see what is going to happen. Now, you know there are always some internal node capacitances, right? So for examples here, internal node capacitor, right? So now you say this node is changing very rarely, right? So that means this transistor is turning on and off quite rarely. So the possibility that this capacitor will discharge, okay, and charge this means basically the charge sharing, right? That issue will be significantly reduced here. But however, if you consider here this one, this is a highly active like input, right? It will keep on changing. As a result, if this capacitor, suppose this node is already charged to VDD, right? Then there will be a tendency of this to get discharged, and also the some way or some type of power dissipation, right? So that way, if you have some highly active nodes, or if you know this some of the input which is very active, then try to keep these nodes as far as possible from this output capacitor, means from this output node. Then glitch reduction is very important. So what do you mean by glitch? Glitch is basically, let us take an example, and from this example, let us illustrate this, what is glitch. So here you can see this A and B input, here it is input E, the input C, right? This is D and E, like A input, right? Say this A, B, and C, like these are type of like same input source has been fed to this A, B, and C. So they are with respect to time scale also, they are changing at the same time, right? But you see here, this is D, right? And D is the input for this next gate. So what is happening, if you consider when this A and B are changing, right? At the same time, these means after some delay, the value of D will change, right? So you see this D value has changed, but for this period, you see this for this period, which is already been highlighted here, right? Here C is higher, C is higher. So for almost for a type of at least for some nanosecond, right? This output of this E will become 0 before it again, right? So this transition is unwanted transition, right? This unwanted transition is called the glitch. And you know, whenever there is an dissipate, means whenever there is an switching, either from on to off or from on to on, there will be some power dissipation, right? So you want this number of glitches to be as low as possible for your low power design. So then suppose we want to implement the function, one function f, right? Which is basically you can like understand what is the function f. Say this scheme 1 and scheme 2, they are basically implementing the same function. So in one case you have the chain structure, in other case you have the tree structure, right? Then definitely you can say here, like for this scheme 1, the possibility of getting glitches will be much higher compared to that of this scheme 2 for this tree structure, right? So this is again to be, you should consider if you are designing and low power circuit. But if you recall from our previous discussion, right? So this is the chain structure and this is the tree structure, right? Here you see the activity. The activity is 0.06. See here the activity 0.23, right? Here for this tree structure activity is much higher. So that means the power dissipation is much higher, right, for this. But is it type of general, like can I make a general conclusion, right, that for tree structure the switching activity would be always higher? The answer is no, because this again depends on the values of PA and PB. So if you change the value of PA and PB, right, then probably for this you could have get lower alpha compared to this. So when you are considering for low power design, it's not only that you should consider the switching activity, you should consider the if there is any possibility by which you can reduce VDD, if there is any possibility by which you reduce alpha, right? Almost all the things you should consider simultaneously, including the glitch, right? So what about glitch in dynamic CMOS logic? Do you think that glitch would be an issue for dynamic CMOS logic? Dynamic CMOS logic output only changes in the evaluation state, right? So that glitch issue should not be a great concern for dynamic logic CMOS circuit, right? Then the some other techniques like gated clock signal. So what do I mean by this gated clock signal? So for example, suppose let us take one. Okay, what do you mean by gated this gated clock signal? Suppose if you have different blocks, right, in a design, if you have different blocks, right? So suppose this is one of the block and which should be which should be operating at all the moment, right? So you have to feed the clock all the times here, right? Because you want the output from this block all the times. However, suppose these are the blocks, this number 1 and number 2. Here, not for all clock period, or for not for this all clock, when the clock is high, you don't want the output, right? You want the output only for some specific time, right? Rest of the time, you do not want the output. Then, do you think that you should feed the clock here as well for all the time? The answer is no, because if you feed the clock here for all the time, then this blocks will also dissipate lot of power, right? And anyway, that you are not taking the output at that time, then why to use this clock here? Then basically you can get this clock getting means you are blocking that clock appearing to that particular block, right? That is basically it's called the clock getting, right? So we have taken one example. For example, we suppose we are making one n-bit comparator. N-bit comparator, right? So even suppose this is the number, okay? Say this is the n-bit, right? So yeah, numbers are same. So here you can clearly see this MSB itself for this number A is higher compared to the other number, right? Then obviously this number, sorry, then obviously this number is the number A is higher than number B. We can decide by comparing this one only. No need to compare the remaining bits. See, when you are not comparing remaining bits, how do you compare? You have to do some operation. You know that you have some, suppose, how do you compare? Which gate will help you in comparison? XOR. So the output has to change, right? So the XOR output has to be changed. So is it really required to check these many numbers? If you can only check the first number and tell that, this number A is higher, right? So here basically we are doing the same thing. You can see it is A n minus 1 because the number starts from 0, right? So B n minus 1. So we are taking the MSB feeding to this gate, right? And if this gate output is equal to 0, right? If the gate output is 0, then only, if the gate output is 0, then this output is also become 0, right? So that means this clock will not be appeared here, right? So that means the remaining numbers, right? 0 to n minus 1, that will not be loaded in registers. After that, that will not be using this n minus 1 bit comparator, right? So you can understand for loading also, you have to just transfer it, right? Some power dissipation. Again for comparison, some power dissipation. So if you can prevent that, then you also save lot of energy, right? Okay. The other example that we have given in terms of D flip-flop. So here, if suppose the input is 0, output is 0, right? If the next input is 0, then is it required to feed the clock? No, right? Because you know that if the inputs are not changing, output is not going to change. So even here, if we consider this is a normal D flip-flop, you give 0, clock fade, right? Output will change. Then again, the clock will fade for 0. Lot of power dissipation, but output is not changing. You are not gaining anything. However, if you consider this block, right, here we have make an arrangement such that this clock will be only fed here if this output and D are different, otherwise not. Then input gating, right? So in clock gating, we are basically preventing the clock to be appeared across some block, right? In input gating, we will prevent the inputs to be appeared across some block. For example, you can see here, this is one block. Say this is performing the addition. Say this is the F2 block. So say this is the performing the subtraction, right? And is the combination logic, right? So whenever A and B will appear at the simultaneously, it will produce, after some delay, it will produce the sum. After some time, after that delay, it will also produce the subtraction, right? It will also produce the difference. But suppose you at that moment you only need the sum, then why to produce the difference? Then we could have block this A and B to be appeared across this F2, right? That way also we can save some energy. So you could have see the next one. See here. So here these are these registers through which this number A and B are been fed. This is that block F1. This is the other block which is F2, right? And here after that these two outputs are connected with a multiplexer, right? And here you have a selection line with the output. So by using this selection line, suppose if you are choosing this addition, then you are only choosing this, right? And at the same time you will make this F1 such that F1 is transparent and this A and B are only applied across this block, not across this block, right? So that way you can save some energy. Then the next one is the pipelining. This is an important concept. So what do you mean by pipelining? So if you have some sequential process, right, and if the next process has to start after the first process, then the third one after the second process, then probably you could have instead of using and type of this single input, single output network, you could have also broken this total task into sub part, right? So you could have broken this. Suppose we have taken an example of this advanced washing machine, right? This washing, drying, and then finally ironing. So instead of purchasing one single machine, you could have purchased 3 different machines which will perform the operation separately. And if you see that after that, so you can see here to wash and iron the n number of clocks, you need total nt time, n into t times time. However, for here this case, for n number of cloths, you need n plus 2 into t by 3 times. So obviously, for the next day, the speed is much higher or the throughput is much higher, right? So now what we will say, if we just break from this to this, our speed will increase, right? But suppose we do not want to increase the speed. Power is the main criteria. Then what we can say? Then probably we can reduce the speed. How can you reduce the speed? If you reduce VDD, then we have seen, right? Then the delay will increase, speed will reduce, right? So basically we will now reduce the VDD. Now when you reduce the VDD, power is by default going to reduce, right? So that was the technique we use in the pipelining. That is the concept, right? The same thing has been applied in terms of suppose some logical operations. How can you prevent you can make this part one block, next part one block, next part one block, right? Instead of making the implementing the total logic function here, you can break it into smaller parts. That will speed up the process, right? But then your argument would be, we do not want to speed up, so we will reduce the speed by reducing VDD. That will reduce the power dissipation. The opposite concept is called the pipelining. I think this is already clear to you. I am not going to discuss it. The next concept is called the pipelining concept. So in pipelining concept is what? Here, really, you cannot split the tasks. Suppose if you have some function addition a plus b, you cannot reduce it. You have to use that function only. So that block is fixed. So now we are saying this, we have an adder. Now we will add different number of adders, or like multiply the number of adders. So here we will use one adder, second adder, third adder, like that, right? Many adders we will add, right? And here we will feed this input through this, right? And then we use the multiplexer and then an register, right? Here again the same thing we will do, same argument we will put. If we use this, then to perform, suppose to perform a by b, okay, by this, okay, then suppose b plus c by this, it has to be fast, right? But if we have multiple hardware, then you could have used fed a plus b to this, then b plus c to this, then the next operation to this, right? But now you see, earlier everything has to be done within a certain time, right? But now you have to only do a plus b within that time. So that way your speed, you can actually substantially reduce the speed of this logic function. So how can you do that? By reducing VDD. That will reduce the power, right? That is the here this concept. Retiming is very easy. Instead of making like uneven timings between these registers which are operated by clock, right? If you use type of make this arrangement such that the delays are almost the same between these two registers which are fed by clock, then you can again speed up the process. Then you can reduce, you have a possibility that you can reduce the VDD. That is retiming. Bus segmentation is basically the, like, instead of connecting all if all the network with a common or global bus, right? You could have actually segment this bus, right, and connect some of the part with that, because whenever you are connecting more number of bus, more number of, like when you are connecting, suppose with a global bus, many devices or many segments, so basically you are increasing the capacitance associated with the global bus, right? If you segment that, then you can reduce it. And power is proportional to C as well. So if you can reduce C, that way you can reduce the power. Then algorithmic level, I will take 2 more minutes, okay? Algorithmic level technique. So here, even before, this is just from the algorithmic level point of view. Say, we want to use, make one binary counter, right? Then you have an option to choose this numbers, the number pattern, say 7-bit binary, say 8-bit binary this counter, right? So you can choose from 001 to 111 all the binary numbers, or you could have used these gray code numbers for that, right? You could, if you have used the gray code number, then you can see from 1 bit to the next bit there is only one change in the from one bit to the other bit. So that way you have only less power dissipation, because here you can see in some cases there are 2, and maximum in some cases there are actually 3 bits are getting changed, right? Then last one is the state encoding FSM. Suppose you are making any arrangement, means finite state, you have to assign the states, either it is 0011 or 01. How do you define it? So in last class we have discussed this, and we have seen that we have to define the states such that the states with which the transition probability are highest, we will assign less number of change between these two states, right? So for example, see here the transition probability is 0.3 and 0.4, and here both 00, this digit and this digit, both bits are changing, right? So here the total transition is 1.6, whereas if you see for this, the total transition become 1, right? So by doing all these things from this algorithmic point of view only, you can substantially reduce the power dissipation, right? So then we are probably not go, okay, I think this part is not that way important. We have discussed it though. So tomorrow we will start either like CMOS latch-off or the sequential logic circuits, okay? Or CMOS latch-off probably will not take much time, maybe half an hour to 40 minutes. Then first CMOS latch-off and then sequential circuit, right? Because tomorrow we have a 2 hours, right? Okay. So yeah, and I will send one handwritten document, okay, today for this, and on also one recorded video on BiCMOS logic, okay? Please do go through that, and if you have any doubt, we can discuss tomorrow as well as in the next class.